In part 2 of our NMR discussions, we're going to be looking at the rest of the information that we can get from NMR. We've already covered signal. So in this section, we're going to be looking at chemical shift, we're going to be looking at integration, and finally splitting patterns. These are all pieces of information we can get from an NMR spectrum. Starting with chemical shift, so every hydrogen in a molecule is going to have a specific chemical shift associated with it, and depending on what sort of local magnetic environment that hydrogen is in is going to give rise to a different chemical shift, and that's the usefulness of NMR. And all these functional groups that we have in organic chemistry, we're going to see that we can quickly spot some of these in an NMR spectrum because they have very specific chemical shifts. So this chemical shift is completely independent of NMR magnetic strength. So the higher magnetic strength magnets, like the one they have at the University of Washington, is a 900 megahertz. I think it's above 900 megahertz, really large magnet, but it doesn't matter because this scale, this chemical shift scale, is going to be the same no matter what the size of the magnet is. So our instrument is described as a 60 megahertz instrument, but there's some really large ones out there too, but there's chemical shift independent of that. By the way, though, the bigger magnets give better resolution of the signal, so that means that the peaks that you find in an NMR spectrum are real tight, they're real crisp, it's easy to see the different hydrogens versus ours, where sometimes the hydrogen signal just really spreads out and overlaps a lot. It doesn't give very good resolution, but it works. That's what we have. So the way you calculate the way you calculate the chemical shift in ppm is you just simply determine the shift downfield from TMS. Remember, TMS is that reference compound that we always put in, and TMS is arbitrarily set to 0, and then everything else that we find in our molecule is downfield from TMS. So if we can measure that value in hertz, we just simply divide by the total spectrometer frequency in megahertz. Okay, so let's take a look at a couple sample problems doing this. Now keep in mind, we never do this actually when we do NMR because the scale is directly the proper scale units when we get our NMR spectrum, but just as a useful exercise, let's go ahead and play with some numbers here and calculate chemical shift. So the chemical shift for this first example, that should have been chemical shift in ppm equals, for this particular proton, we saw that it was 65.6 hertz downfield from TMS, so relative to TMS, it's 65.6 hertz downfield. And if our instrument at Shasta College is 60 megahertz, I think I did this in the calculator earlier. I think I got something to round to 3 sig figs. I got 1.09, and this is in the units of ppm at this point. Okay. So in our NMR spectrum, we would expect to see a signal at 1.09 ppm, and that's downfield from TMS at 0. Now let's do another calculation. This time we're going to assume that we're dealing with 300 megahertz NMR. When I was at Cal Poly, I had a chance to work on this briefly in advanced organic chemistry laboratory, and it definitely gave better resolution. So we're going to do the same type of calculation by saying chemical shift, once again in ppm, equals, and in this case, we found a resonance at 328 hertz for some particular proton divided by 300 megahertz. And lo and behold, when I do this calculation, guess what? It's still 1.09 ppm. Okay, just because the magnet is bigger, it's a bigger instrument, the chemical shift ultimately is the same because the way we calculate this, that's all factored in. Okay, so it doesn't matter what the size of the magnet is. All right, so I think I've proved my point here, but from this point on, we always report shift values in ppm. We don't ever do this calculation. Okay, so let's talk about an actual NMR spectrum. I'm not sure that we've seen one yet, but here's one I did of a molecule. It's called dimethoxymethane. Here's the molecule structure here. And the scale, the delta scale, so to speak, is in the units of ppm. And strangely enough, the scale is 0 on the right side and 12 way down here. Probably this is not the best example I should be presenting because I've arbitrarily zoomed in on the spectrum. I kind of cut down the scale, but traditionally the scale goes all the way out to 12 ppm down here on this side. Now this is weird too because we're used to starting 0 on the left side and then going to 12 on the right side, but that's just not how it works, okay? And then of course this little peak right here, it's tiny in this case, but that's the TMS peak, and we set that peak, that signal to be 0, and then all these peaks down here are downfield from the TMS. Now, just to do a couple of peak assignments, we're going to be doing this quite a bit. For this molecule, I can tell you that the 6 hydrogens that are represented by this signal right here are going to be the 2 methyl groups. So here's one methyl group, here's another methyl group. They are magnetically equivalent methyl groups, and that's why they're kind of lumped together at this shift. And if we read this scale here, we say that it's 3.2468. This looks to be 3.3 ppm is the value for this. That's pretty typical for hydrogens that are attached to a carbon that are adjacent to an oxygen. Remember, these are fairly de-shielded protons because of the oxygen being electronegative. But even better is this central methylene group with 2 hydrogens. This one's even more de-shielded. And that's that signal right there, and that's 2 hydrogens for that peak. And this chemical shift is 2, 4, this is about 4.5. So why is this one more de-shielded? Because it's sandwiched between 2 oxygens, which are both withdrawing electrons. Okay, so these are even more de-shielded. All right, so that's how the scale works. So 0 on this side, ppm, and then 12 ppm on this side. The reason why we always add this reference compound again is because we want to shift the scale properly. There's a tendency for the NMR to kind of drift over time as the room heats up, cools down. That's why you always have to be watching to see that TMS is on 0. Okay, so some more terminology. I think we've mentioned this several times in class. The 12 side of this scale is considered downfield. These are going to be the de-shielded protons. And the 0 side is considered the upfield side. These are shielded protons. And remember, the protons of TMS are the most shielded you can have because of the silicon. Okay, so why would protons be more or less de-shielded? And we've started to lay the groundwork for this, but let's consider a molecule like methane. And the actual chemical shift is pretty close to 0 for all 4 of these hydrogens, which are magnetically equivalent. The delta, or the shift value in ppm, is 0.2, so it's very near 0. It's not much further away from TMS than, TMS is at 0, and this one's not too far away. Now, if we add a chlorine atom to this molecule, what happens is, with the chlorine being very electronegative, the electrons are pulled this direction away from the carbon, and therefore the electrons are pulled away from the hydrogens. So we say that these hydrogens are a little bit more de-shielded compared to these hydrogens right here. And notice that the delta value, or the ppm value, increases, and we start to move away from TMS. In fact, the difference between no chlorine and having 1 chlorine is pretty substantial at 2.8 ppm. Now let's add 2 chlorines to the molecule. And of course, now there's even more de-shielding of these 2 hydrogens, and their value is 5.3 ppm for this, and that's a difference of 2.3 between these two. It's almost double what this difference was. Almost, not quite though. And then now we add 3 chlorines. This is chloroform, and now we've got all these chlorine atoms withdrawing electrons in this direction, and that tends to really de-shield this hydrogen. Its value is 7.2. Okay, so every time we add a chlorine, we're increasing the amount of de-shielding for the hydrogens that are remaining. Okay, and you're always going to find this with electronegative atoms. They tend to do that. They tend to de-shield hydrogens as a result. Now, hydrogens attached to or near electronegative atoms, I've already started to talk about this. So we saw a chlorine example just a second ago. Now let's look at this butane molecule, and here's the normal shift values for all the hydrogens. Now these methyl groups on the end, these are magnetically equivalent. They're both 0.9 ppm, fairly close to TMS because they're fairly shielded. There's nothing special about these. Same goes for these CH2s, these methylenes. They're not much different from the methyl groups. They're fairly shielded, nothing going on here. Now, as soon as we replace one of these N hydrogens with a bromine, notice what happens to the shift values. They're all different because the molecule is no longer symmetrical at this point. And the closer you are to the bromine, which is having the effect of withdrawing electrons in this direction, that tends to de-shield the hydrogens that are closest to the bromine. That's why this value is 3.4. I mean, it's not a really huge number, but still we get a little bit of de-shielding. Now, as we move away from the bromine, notice that the effect diminishes. So this one is now 1.7, this one's 1.3, and this one's 0.9. So this effect very rapidly diminishes as we get further and further away from the bromine. That's because it's an inductive effect, not as powerful as some of the other effects we've seen in the past. Okay, so this methyl group and this methyl group are the same. This one's so far away from the bromine that it's the same as this one. Okay, so that's electronegative atoms. That's their effect on the amount of deshielding that a proton experiences. So let's go back to an example HNMR spectrum. We've already seen this spectrum before, and let's just redo this assignment. So these two methyl groups at the ends are both magnetically equivalent, and that's why they're both represented by this signal right here. So one signal for both sides. And they're fairly close to an oxygen, so that's why they're not down near TMS. They are actually more like we already said this before, but they're like 3.3 ppm, and that's due to the effects of the oxygens, which are pulling electron density towards them, and that tends to deshield the hydrogens, and that's why the peaks are here. Now these central CH2, this methylene group experiences this even more because we've got two oxygens each pulling electrons away from these hydrogens, so in that direction and this direction, and that's why this value is about 4.5. Because the effect is even stronger. These two hydrogens are sandwiched between two oxygens, so really deshielded compared to the N ones. Okay, so that's what electronegative atoms do. They tend to deshield protons, and the closer these protons are to the electronegative atoms, the stronger this effect is going to be. Let's talk about aromatic hydrogens. So some interesting things happen when you have hydrogens attached to, say, a benzene ring. That's what this is. Now, benzene, just as a reminder, let me just draw this in so this is abundantly clear. Benzene, of course, has these double bonds, and every one of the carbon atoms in the benzene ring is sp2 hybridized, which means that every carbon atom effectively has an unhybridized p orbital, and p orbitals look like so. And what happens in this system, this is a special system, it's called an aromatic system. There's a whole chapter devoted to aromatic systems a couple chapters from now, so we'll get to more gory details of this. But what tends to happen with all these p orbitals is the electrons just simply flow through these p orbitals above the ring surface, but also below the ring surface too. And the main point here is that with circulating electrons like this, and so we're saying that the circulating electrons are going counterclockwise in this situation, those circulating charges tend to create a little local induced magnetic field of their own. And now what you see due to the electrons are these green lines. This is a magnetic field. And what happens is the hydrogens, which are coplanar with all these carbon atoms, they're in the plane of this ring, they're experiencing an induced field that reinforces the external field. So that's a deshielding effect. And therefore these protons, these hydrogens at the end, or that are bonded to the benzene ring, they're fairly deshielded. So we're going to see that the chemical shift for these hydrogens is approximately 6.5 to 8.0, although there's exceptions to that, of course, but that's where they end up. And that's pretty far away from TMS as things go. Okay, so that's the effect here. It's these circulating electrons that create this local magnetic environment such that these field lines right here are reinforcing the external field, and that's why they're fairly deshielded. Okay, so that's aromatic hydrogens. So anything that's benzene-like and where you see hydrogens attached, you can expect the shift values to be 6.5 to 8.0, so a fair distance from TMS. Same goes for vinylic hydrogens. So remember, the terminology is that if this is a double bond, anything that's directly attached to one of the two carbons making a double bond is referred to as vinylic. So these two hydrogens are vinylic hydrogens. And in this situation, it's very similar to the aromatic compound. There's electrons. This is a p orbital here. This is a p orbital, p orbital, p orbital. These are sp2 hybridized. So there's electrons above and below. That's the definition of a pi bond. And with these circulating electrons above and below, once again, we see this induced local magnetic field caused by the electrons circulating around, and this also reinforces the external field, although the effect is not quite as strong as aromatic compounds, and because of that, the shift values are typically 4.5 to 6.5 ppm. But the effect is similar to aromatic compounds, it's just not quite as strong, and this is the shift value that we expect. Okay, so vinylic hydrogens, somewhere in the neighborhood of 4.5 to 6.5 for the shift value. Now, triple bonds are kind of a strange beast because the hydrogen ends up along the bond axis. You have no choice with a triple bond. This is a triple bond right here. Okay, triple bond. And remember, the bonding is quite complicated. There's a p orbital that goes this direction, so bonding above and below. But then there's another p orbital that's coming out towards us, like so, and there's bonding above and below that one as well. So the triple bond, that's how it works. So there's a lot of electrons that are circulating in this direction. But the field lines that are created are such that the hydrogen's not really in the middle of these field lines. It's kind of along the axis. And so the deshielding effect is really not that strong, actually, compared to aromatic compounds and vinylic hydrogens that we just saw a second ago. So the typical values for alkyne hydrogens are somewhere in the neighborhood of 2.5 to 3.0. So now we're talking about hydrogens that are starting to be more similar to TMS shift values. Okay, so this effect not so strong. So this one's an interesting one. So this is an aldehyde functional group. Aldehydes are super easy to spot in an NMR spectrum because the effect here is with this pi bond, here's the field lines. This hydrogen is extremely deshielded. The values typical of aldehyde hydrogens, and only the aldehyde hydrogen, somewhere in the neighborhood of 9 to 10. Nothing else in molecules appears in that range, and that's why aldehydes are super easy to spot in NMR spectrum. So easy to spot that in the next laboratory experiment, or if we're already doing it, the aldehyde, let's see, it's called the oxidation puzzle, and one of your jobs is to figure out how much oxidation occurred in a molecule, so you're going to have to figure out whether a ketone was produced or an aldehyde, and I strictly forbid you to use NMR because NMR would really tell you pretty quickly whether the molecule became an aldehyde or something else. Okay, you're only going to use IR to do that, but NMR would be really quick and easy. Okay, so the effect is fairly strong here, a lot of deshielding of this hydrogen, and the values are 9 to 10. Nothing else except for aldehyde hydrogens appear in that region. Really easy to spot. What about hydroxyl and amino hydrogens? These are kind of tough ones because they can be all over the place. I wish I could sit here and say that they're in one specific location, but there's a lot of things that can happen with the hydrogens attached to oxygen or amino groups. Amino groups, by the way, are NH2 groups. So chemical shift depends on concentration is the first bullet point that I'm going to make. So depending on whether they're diluted samples or they're pure samples, can have really strong effects on where exactly you see the chemical shift for that hydrogen. Now, typically, hydrogen bonding tends to deshield the proton, and typically the chemical shift is 3.5 ppm for NH and 4.5 for ppm for OH. But there's a lot of exceptions to this. Sometimes, most of the time on our NMR, it's pretty easy to spot OH because they tend to be broad signals. They tend to look really smooth. They're not usually coupled to other hydrogens. And so even with this being said that it's kind of, there's an exception to this rule a lot of the time, they're still fairly easy to spot just simply because of the shape of what this signal looks like. Another thing that's occurring too with OH and NH is proton exchanges between the molecules broaden the peak, and that's what I just said a second ago. These are still easy to spot because the peak is definitely broader than some of the other CH peaks that we see. All right, so this is kind of hydroxyl and amino hydrogens, typically these values with a big but. Okay, a lot of exceptions to this rule. The last group that I want to mention are carboxylic acids. So just like aldehydes, the effect of all this resonance, this pi bond, all these circulating electrons is such that the hydrogen of the carboxylic acid is highly, highly, highly deshielded. So much so that somebody made this spectrum and they made the scale 0 to 10, but the truth is this hydrogen appears more like 12. And so they said this little offset statement, meaning that the hydrogen signal is off scale by 2.0 ppm. So it's over here somewhere. Here, I'll just sketch it in for you. How about that? It's over here. It's actually off screen, okay? All right, so very strong deshielding effect for carboxylic acids, and that's why they're always distinctive in the NMR spectrum as well. You can really spot those. Nothing else appears above 10 except for carboxylic acids. The other part of this molecule, of course, is the methyl group, and that's the signal down here. So it's fairly close to, well, it's kind of close to oxygen. That's why it's not close to TMS. So it's a value of about 2.1, which is pretty typical of hydrogens that are 1 carbon removed from a ketone carbon. Pretty typical value. Now, without talking about the remaining functional groups, I'm just going to simply at this point give you a list. This is a table of typical shift values for different types of hydrogen and molecules. You're always going to have this table available to you on exams. I passed out the spectroscopy unknown determination guide to you, and this very table is in there. So you don't really have to memorize these values, although it really helps to have them at the back of your mind, so that way you don't have to go searching for them on a test. But anyways, just to march through these really quick. So typical values for methyl groups somewhere near TMS, of course, this is TMS, is set to 0. Methyl groups are pretty close to that at 0.7 to 1.3. Methylene groups, CH2s, not too much different than methyl groups, 1.2 to 1.6. This is sometimes called methine. So one hydrogen attached to a carbon, 1.4 to 1.8. All right, so allylic is the position one carbon removed from the double bond, and the hydrogen that's attached to the allylic carbon is somewhere in the neighborhood of 1.6 to 2.2, so still fairly close to TMS. Methyl ketones, so this group specifically is typically in the range of 2.0 to 2.4. I will mention at this point that you can quickly spot contamination from acetone. Some of you already took through the exercise of washing your NMR tubes, and I told you to let the NMR tubes sit around for a couple of days to dry off, because if you don't do that, acetone, which is a typical ketone, shows up very distinctly at a value of 2.1. You don't want that in your spectrum. It's contamination. Aromatic methyl groups, so this is a carbon removed from the benzene ring. The hydrogens that are attached to this, 2.4 to 2.7. Alkynyl, we talked about this already, 2.5 to 3.0, somewhere in that range. Alkyl halide, so the halide is a fairly electronegative atom, especially if it's chlorine. The hydrogen that's attached to the same carbon is 2.5 to 4.0, depending on what exact halogen is attached. Alcohols, a very wide range for alcohols. I wish I could say that it's one value, but it's not. It's a wide range, 2.5 to 5.0. Alcohol and ether. So what we're saying here is that if this is hydrogen right here or carbon, it doesn't really matter. So if this is an ether or alcohol, the carbon on the other side has a hydrogen. Its value is 3.3 to 4.5. Okay. Vinylic, we talked about 4.5 to 6.5. There's really not a whole lot else that falls in the same range. So if you see something 4.5 to 6.5, you can assume that it's a vinylic hydrogen. Aryl hydrogen, so aromatic hydrogens attached to benzene, we already mentioned 6.5 to 8.0. Aldehyde, very distinctive. I would argue that the range is somewhere between 9 and 10, not 9.7 and 10, but there you go. Carboxylic acids, 11 to 12.0. I think I said before 10 to 12, but nothing else really applies. It appears in that region. All right, so the third piece of information we get out of NMR spectra, and here's the same molecule again, is when we integrate the peaks, meaning that we find the area underneath these peaks, the area is proportional to the number of hydrogens that are represented by the signal. So this is a pretty good molecule to be working with because, let's circle these hydrogens again. So there's two hydrogens in the middle of this. We already stated that these two hydrogens are represented by this signal. And notice that I've already integrated this. I did this on the computer, and I set the integration value to be 2, which is appropriate for the two hydrogens that are here. The same integration happened for this peak, which is represented by 3 plus 3 is 6 total hydrogens. Okay, so when we integrate, these areas underneath the curve are proportional to the number of hydrogens that are represented. So we always integrate hydrogen NMR. Now, I should mention at this point that when we do carbon NMR, we never integrate carbon NMR peaks for reasons I'll get into in part 3. But hydrogen, we do this, and these are the numbers of hydrogens. Just a couple more examples of integration, just so we're clear. Here's a molecule. This is, this one's... what is this called? 4-bromocetophenone. And we've got hydrogens here, 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 and here, and then also a group of hydrogens here. Now, when we first look at this molecule, it's tempting to say, well, it is true that there's 3 different types of hydrogen. Here's one type of signal, here's another type of signal, and here's the third type of hydrogen. These are equivalent on both sides. Now, why is it that we only see 2 signals here? It's because, well, this is the methyl group. but it's because that these two signals here and here, they're just so close together in the spectrum that they just appear to overlap in this region right here, and that's why we can't really tell the difference between the two. And also this pattern right here is called a complex pattern. We'll get into that in part 3. But nonetheless, both these signals are represented by this total peak. That's also why I integrated this as one giant lump sum, even though there's two types of hydrogen represented by this. So here we go. So here's the methyl group. Its integration is approximately 3. It's not perfectly 3. You rarely get perfect values, but it's close enough to the 3 that I'm pretty confident that this signal is this one. And then likewise, all 4 of these hydrogens are represented by this. And notice that the integration is about 4 right here for these 4. Okay, so the grand total, of course, is 4 plus 3 is 7 total hydrogens. That's exactly what we have in the molecule. 3 plus 4 is 7. Here's paraxylene. So paraxylene has 2 methyl groups, and they're both represented by this one signal. And the integration value is 6, of course, which means that there's 6 hydrogens represented. And the remaining 4 hydrogens are all chemically equivalent. They're all magnetically equivalent, are represented by this signal right here. Okay, so that makes total sense. 6 plus 4 is 10 total hydrogens. That's exactly what we have in this molecule. So integration is pretty easy to understand. We just integrate the area underneath the curve. It's proportional to the number of hydrogens. So when you look at your unknown NMR spectra, those integrations that I did for you, those are actually the number of hydrogens that your molecule has, and so you can count on that to be pretty accurate. Okay, so let's move on to the most complicated aspect of NMR, and that's the splitting patterns that we see in these spectra. So splitting is also useful information. This is the 4th piece of information that we get from spectra. And these hydrogen signals in an NMR spectrum are frequently showing splitting patterns that is caused by hydrogens on adjacent carbon atoms. So we're going to see there's yet another effect that causes the local magnetic environment to change a little bit depending on how many neighboring hydrogens there are, and this is called splitting. So we've already seen examples of some splitting. There's some strange things that we saw just a second ago in a spectrum that I presented to you. It was the acetophenone one, and we're seeing elements of splitting. We're going to use the what's called the N+1 rule for predicting what the splitting pattern should be for a given hydrogen in a molecule. These splitting features are also known as multiplet patterns, meaning that the signal that we find for a hydrogen often is represented by multiple little peaklets, or whatever you want to call them, multiplets. Okay, they're called splitting patterns. Okay, so we're going to march through some examples on how this all works. I'm going to give you the basics as the first thing I do, march you through some examples, and then later I'm going to get into the theory why splitting occurs and what's going on with splitting. So now let's do the easy stuff first, the N+1 rule. It's best to just simply look at a molecule to explain this, the N+1 rule. Here's a molecule. This is an ether. It's a fairly easy molecule. Let's just ask the simple questions first. How many different types of hydrogens are in this molecule? So how many signals do we expect to see in the NMR spectrum? And the answer is we expect to see 3, and that's exactly what we get in this computer-generated spectrum is 3 signals, except that they look weird, right? And they look like, it actually looks like there's 1, 2, 3, 4, 5, 6, a bunch of signals, but no, actually what's going on here is one signal are these 2 methyl groups, and all 6 hydrogens that are attached are represented by what we call a doublet. And then there's a hydrogen here, which is the next signal. That one is represented by this multiplet right here. So that's one hydrogen represented by this extremely weird-looking peak right here. And the last methyl group is represented by this peak, which we call a singlet. So here's how the N+1 rule works for predicting what these things should be. And by the way, the terminology is this. So if I see 2 little peaks that are side by side like this is called a doublet. This one's called a singlet because it's a single peak. And if you look really closely, if we count this up, 1, 2, 3, 4, 5, 6, 7, this one's called a septet because it's got 7 little mini peaks contained within it. All right, so let's clear the screen. Let's look at this again. So here's the analysis. Let's start on this side. I guess we'll start on this side. So there's hydrogen, 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 and 3 more down here. Remember, all 6 of these hydrogens are the same signal. They're magnetically equivalent, so they show up as one signal in the NMR spectrum. all 6 of them have one neighbor hydrogen. What I mean by neighbor is here's the hydrogens here, here's the hydrogens here, and if we go 1 carbon remove from either one of these carbons, we get to this carbon, and there's 1 hydrogen attached to this. Okay, this carbon right here. So all 6 of these, so to speak, have 1 neighbor hydrogen. And what the N+1 rule says is that since all 6 of these hydrogens have 1 neighbor, it's 1 neighbor, we say that N is 1 plus 1 is 2, and so therefore we predict that the signal for all 6 of these hydrogens is a doublet, and that's exactly what this is. This is called a doublet because they have 1 neighbor, N+1 doublet. Now let's do the same analysis for this lowly little hydrogen right here. How many total neighbors does this hydrogen have? So we look to the adjacent carbons, and this hydrogen has 6 total neighbors. There's no neighbors here. And with 6, and we use the N+1 rule, we predict a septet, so 7 little mini peaks, and that's exactly what we see here. If you count this again, you're going to see 7 little peaks in this. And then finally, the last methyl group is here, so that's these 3 hydrogens. How many neighbor hydrogens do these 3 have? Well, the answer is none. This is an oxygen with no hydrogens attached. So really the N+1 is 0 plus 1 equals a singlet. That's exactly what we see. So these are called splitting patterns, sometimes known as multiplet patterns. This is a singlet, this is a septet, this is a doublet. This is one signal for the 3 different types of hydrogens. Okay? So that's splitting. I think I have a couple more examples before we're done with this. Yeah, here's another example. This is another computer-generated spectrum. It's unfortunate because these things are really hard to see. Hopefully you can see that with the high-resolution video that this is. Okay, so first dumb question is, how many different types of hydrogen do we expect? How many signals do we expect? Here's 1 type of signal, or 1 type of hydrogen, 2, 3, and 4. By the way, this is not a diastereotypic. These are not diastereotopic hydrogens. They're not, nor are these diastereotopic. So it's just 1, 2, 3, 4 signals. That's exactly what we see. All right, so what should the splitting patterns be? What should the multiplet patterns be? So let's start with this N-methyl group, which I suspect I probably should have drawn the molecule the opposite direction because this methyl group is represented by this peak right here. It's the furthest away from the oxygen, so I suspect that it's the most upfield from everything else. Also, I can tell that it's probably this peak 2 because when I do the N+1 rule, I see that the number of neighboring hydrogens to these 3 is 2 neighbors. 2 plus 1 is 3, so we predict that the signal for these 3 is a triplet, and that's exactly what we see here is a triplet. Likewise, for this CH2 group, I suspect that it's this signal right here in the peak assignments because these 2 hydrogens have 3 neighbors, and with 3 neighbors, the N+1 rule predicts that this should be a quartet, and that's exactly what this is. It's a quartet. Moving on, these 2 hydrogens are these 2. And with no neighbors, excuse me, they do have a neighbor. So these 2 hydrogens have 1 neighbor. That's this hydrogen that's attached to this carbon. We predict that these are going to be, the signal for this methylene group is going to be a doublet. That's exactly what it is a doublet. And the final type of hydrogen is the aldehyde hydrogen. That's going to be this one. The signal's way down here. Remember, aldehyde hydrogens are between 9 and 10. This one's predicted to be with 2 neighbors, N+1. It's predicted to be a triplet. That's exactly what it is down here. Okay. So this is another example of splitting patterns, and these are, unfortunately, these are normal molecules, so we're going to see that the N+1 rule works fine for these types of molecules. In part 3, I'm going to get into more complex patterns. Some weird things can happen beyond what's already weird. Okay, splitting. So that's another piece of information we can get from NMR. It tells us, for each signal that we find, it tells us how many neighboring hydrogens are in the molecule. Here's an actual example of an NMR spectrum for this molecule. So once again, we're going to ask the stupid questions first. So for these 2 methyl groups, they're magnetically equivalent, so they're represented by 1 signal. And when we look to the adjacent carbon, there's no hydrogens attached to this. So we predict for all 6 of these hydrogens, we're going to predict that it's a singlet, and that's exactly what it is. Okay, here's a singlet. For the OH is going to be this signal right here. And there's no neighbor hydrogens right here, and so this is a singlet. Remember, too, that hydroxyl hydrogens are somewhat broad, and that's why I'm pretty confident that this broad peak right here is represented by this hydrogen. This CH2 right here has no neighbors on this side, but it does have 3 neighbors on this side, and so the N+1 rule says that this is going to be a quartet. Now, unfortunately, since this is a real spectrum, you can't really see the quartet because it looks like it's merging into this singlet right here. Oh, maybe it's here. So here's one little bump, 2, 3, 4. Yeah, I guess the quartet's there. Okay, and then finally, the methyl group is this triplet right here. So with 2 neighbors, N+1 says it's going to be a triplet, and that's that triplet right there. Now, this is not the prettiest looking spectrum because this was done on our lowly 60 megahertz instrument. That's why these peaks are fairly mashed together. That's also why I had to integrate them as one lump sum, 11 hydrogens, and those 11 hydrogens are going to be, 6 plus 2 is 8, plus 3 more is 11, and then there's the 1 hydroxyl hydrogen right here. On a 300 megahertz instrument or a 900 megahertz, even better, we're going to see clear resolution of these peaks. Not true on our little 60 megahertz NMR. But here's real spectrum. This is the analysis looking at the splitting patterns. All right, so that's the how it works. Why does splitting occur? And this is more complication to the picture that is NMR. So we've already talked about quite extensively in NMR discussions the value of delta E, that's the gap between the alpha spin state and the beta spin state, is dependent on both the strength of the external magnetic field and the amount of shielding that the circulating electrons provide. We talked about this quite a bit, and that gives rise to chemical shift. That's why there's differences, yada, yada, yada. Here's another complication, though. So this is something we haven't mentioned before. In addition to those 2 effects that we just mentioned, for a given proton, its resonance frequency also depends on nearby protons that, so to speak, couple magnetically to the current proton under study. So this is what's going to give rise to splitting patterns. There's a third effect that's going on here. It's neighboring protons that couple to the proton under study. So nearby protons generate small magnetic fields on their own that can reinforce the external field, or they can oppose. Let's take a look at a real molecule, see how this works, see what's going on with splitting patterns. Now, I stare at these pictures over and over and over again. I'm going to warn you right now that sometimes it's really hard to understand these pictures, but this is what we need to do to explain splitting. So if you don't quite get this, not a big deal. But here's a molecule. This is a typical molecule when studying splitting patterns. It's got a bunch of bromines, which don't show up in NMR. Only the hydrogens do. This is a hydrogen right here, even though they didn't write in hydrogen here. It's a hydrogen atom. And when we're looking at the signal, and this is the confusing part, so we really have to concentrate when we look at this. These 2 hydrogens right here with 1 neighbor hydrogen, it's predicted to be a doublet for this one signal with 1 neighbor. So that's exactly what we see here. It's a doublet for these 2 hydrogens. These 2 hydrogens are 1 signal, and they're a doublet because they have 1 neighbor. Now, because these 2 hydrogens each have this neighbor can actually be, at any given time, this neighbor, its spin can be aligned with the external magnetic field, or it can be opposed, and that makes a big difference because when this reinforces the field, the shift is further downfield from TMS. On the other hand, if the neighbor hydrogen, its spin is opposed to the external magnetic field, that tends to shield these 2 hydrogens, and that's going to make it more upfield. Okay, so that's why we see a doublet. It just depends on at any given time, whether this is reinforcing or opposing the external magnetic field. This is the neighbor hydrogen right here. This is the signal for these 2 hydrogens, but the neighbor has an influence on the exact resonance frequency for these 2 hydrogens. Okay, so this is called a doublet. It's because these 2 have this neighbor. N+1 says doublet. It's even more complex with this picture. So here's, now we're looking at the other hydrogen. So we're looking at this hydrogen, and this hydrogen has 2 neighbors, so therefore we predicted to be a triplet. And the essence of this is, and this is really confusing, is that this hydrogen is this signal right here. It's this entire signal. But its neighboring hydrogens, since there's 2 of them, there's now 4 possible orientations for the spins between these 2 hydrogen atoms. So on the one hand, these 2 hydrogen atoms can have, each one of them has their nuclear spin reinforcing the external magnetic field, and that's why this little tiny peak right here is the furthest downfield. Okay, it's when they're both reinforcing the external field. The most common situation, though, the most likely situation, is that one proton is reinforcing, the other one's opposing, and likewise, one's opposing, one's reinforcing. So that's the most likely situation, and that's why this middle peak right here is the most intense, because there's two possible orientations for nuclear spin for these two, and they're both energetically equivalent to each other. And then finally, there's a chance that both these nuclear spins are going to be opposed to the external magnetic field, and that's why this little peak is the furthest upfield. Okay, so that's why it's a triplet, because it just depends on how the spins are orientated for these two neighboring hydrogens. We're really looking at the signal for this one. It's a triplet, and it's because there's a couple of different possibilities for the spins of these two, and they can have a big influence on what the chemical shift is for this one. So that's the essence of why splitting occurs. I wish that were the end of the story, but there's also the N+1 rule applies to most situations, but in part 3, and this will be ready for Friday's lecture, in part 3 we're going to talk about even more complex splitting patterns beyond the N+1 rule. But for now, this is our discussion. This is how it works. It has to do with neighboring hydrogens and their spins. Now, these multiplet patterns just kind of rehash this again, so the N+1 rule again. Let's look at yet another molecule and predict the multiplet patterns. Let's start with the end methyl group. So all 6 of these hydrogens are magnetically equivalent, and there's one signal for all 6 of these, and that signal is going to be described as a doublet, okay, because there's one neighbor hydrogen, and the doublet, the way I can quickly predict what the shape of this doublet is going to be is it's going to look like sort of like this. Okay, the doublet is such that the two little mini peaks are equal height, and you can quickly predict what this is going to look like by considering what Pascal's triangle looks like. The way this works is for a singlet, it's just one peak, but for a doublet, the intensity of both these little mini peaks is equal intensity, so 1 and 1. And that's exactly what we see here. So the intensity is equal for both of these because it's equally likely that that one neighbor hydrogen is spin up or spin down. That's why they're equal intensities. Let's move on to this hydrogen right here. So this is one signal, and we predict that this little multiplet pattern is going to be quite complex because it has 3, 6, 8 total neighbor hydrogens, and the N+1 rule says that wow, that one's going to be a, what do we call this? We call this a nonette. I don't even know if I could draw this. Okay, nonette is going to be boom, 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 boom. 1, 2, 3, 4. And then I think the central one is going to be the biggest, and then it's going to gradually drop off like so. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, wow. I guess the right time. Okay. Now, we could have predicted this from Pascal's triangle. Unfortunately, it doesn't even go up to 9, but this is what it would look like. The middle signal would be the most intense, the most likely in terms of spins for neighboring hydrogen nuclei, and then it kind of fades off on either side. So this multiplet pattern is called a nonette for this one. 8 neighbor hydrogens, so therefore the pattern is nonette. Now it gets simpler again, a little bit simpler for these two hydrogens. So one signal for both of these. These are not distereotopic hydrogens, by the way. It's one signal, and the number of neighboring hydrogens for this is 3 plus 1 is 4 plus 1 more. The N+1 rule says that it should be a pentet. So now we can, a quintet. So when we go to this Pascal's triangle, we predict that the intensities for this multiplet pattern are 1, 4, 6, 4, 1, and that's what I'm going to try to draw for this. Okay, so 1, 4, 6, 4, 1 is what this is going to look like. And then finally, the last remaining methyl group here is going to look like, with 2 neighbor hydrogens, it's going to look like a triplet. And this one's pretty easy to draw. That's what it's going to look like. Okay, so that's what they're going to look like. That's what we're looking for in NMR spectra. And this is under a normal situation where we don't have any funny business going on. I keep saying this over and over again. In part 3, we're going to look at more complicated situations, but in the simplest stuff, N+1 rule works great, and this is how you would consider the multiplet patterns to be, is by considering Pascal's triangle. All right, so as a prelude to part 3, we're not going to start this today, but we just talked about N+1 rule and splitting patterns, and all the molecules that we've studied so far are just normal situations. The N+1 rule works great, and there's nothing to worry about, but unfortunately there's some more complicated examples out there, so let me just kind of give you a little taste of something that's coming up in part 3. This is called cinnamaldehyde. I love this molecule, and you can understand why, because it smells great. It smells like cookies and Christmas time and all that kind of stuff, cinnamaldehyde. Unfortunately, when you look at the actual spectrum for cinnamaldehyde, I'm just going to draw your attention to this little detail in that this hydrogen right here, believe it or not, is represented by this signal right here. And normally you would predict with the N+1 rule that this hydrogen with two neighbors, here's one neighbor here, one neighbor here, normally you'd predict a triplet, and quite clearly this is not a triplet. In fact, it's not even a quartet. This is called a complex signal, and the way we really describe this is it's called a double doublet. And that's why all four of these little mini peaks look equal intensity, because there's something weird going on. The N+1 rule does not correctly predict what this one should be. On the other hand, though, this aldehyde hydrogen is correctly predicted to be a doublet. So there's no funny business on this one. N+1 rule works fine. Likewise, I believe for this hydrogen, I think this one's fairly straightforward. I think it's a normal signal, and it's somewhere in this neighborhood right here. And then we'll talk about aromatic hydrogens next time. So as a prelude to part 3, we're going to have to deal with this situation. Why is this hydrogen not correctly predicted in the NMR spectrum?